DIFC, physics, mechanics, and where are we? Kinetic and potential energy. Here we are here. So last time, previously in physics, we stopped on discussion of negative potential energy. What does negative potential energy represent?
Trapped.
It's trapped. Positive means it has the ability to do work, and zero means it's freed. Okay. So let's just continue that. So we were finishing here last time. Do you need to write any of this down? We were a bit rushed at the end. Did you get this last time? Yeah. Okay, let me just save the video here that I'm doing. The first one was physics tutorial, mechanics, work and pressure. Okay. Right, so I can go past this? Okay, quick. So, you were asking me last time, if your hands are tied, does that mean you have negative potential energy in the ropes? And it does, because you require energy to be free, to break them, so it has negative.
Energy.
You have to give it energy to break it. It's just like the electron trapped in the orbit. To free the electron, you must give it energy. So we say it has a negative potential energy.
But then if it was given energy but not enough to let it out, is it still potential energy?
Yeah, it's still negative. It'll just move to a higher orbit.
No, like if my hands were tied and like I was trying to get them out, like the process of getting it out, is it potential energy or what?
It gets a bit complicated. We haven't talked about efficiency yet. So efficiency is something that will come up later. Okay. Now relax. Right. The conservation of energy, which we discussed last time, means that the initial energy of an object, it must be equal to the final energy it has, provided, of course, no energy leaves the system. So as long as you don't put energy in or take energy out, then what you have at the start, you should have at the end. As a formula, it basically means that the energy at the start equals the energy at the end, or the kinetic plus potential at the start equals the kinetic plus the potential at the end. So if you can note this, and we'll have a look at an example. He doesn't like to write things in my class. Again, could you not have the paper out to at least pretend? Remember, I like when you pretend to write at least. Thank you, I feel so much better now.
The E stands for energy?
Yeah.
So energy at the start is equal to the energy at the end.
You got this? Yep.
No.
Okay. Well, I have to answer a question, then I'll continue, yes?
But then kinetic energy can be changed into like heat.
Yeah. So this is what I mean by as long as no energy leaves. So if it becomes heat energy, then it leaves the system then. Okay. A 1 kilogram ball is dropped from rest from a height of 10 meters. What is its potential energy? Let's do this one together. So, yeah. Times 10, yes. Here's the ball, 10 meters high, and it's 1 kilogram. It has potential energy here by using the potential energy formula, MGH, that we did last time. We get 1 times, you don't need the calculator for this problem, 1 times 9.81 times 10, which is 98.1 joules. Okay, so this is part A. Now, part B, how much kinetic energy does it have initially? Why 0? At the beginning it has no kinetic energy. 0. C. How much potential energy does it have when it hits the ground? So when it's down here, the part C, its potential energy is 0 because it has no height, it's on the ground. So then D is what kinetic energy does it have when it hits the ground? No,
98.1.
that too. Because the kinetic plus the potential at the start must equal the kinetic plus the potential at the end. So the kinetic at the end has to be 98.1. Now, if you calculate the V, we'll get the same answer. Let's see. U is, no, let's see. U is 0, V we don't know, A is minus 9.81, T we don't know, and S is minus 10. V squared equals U squared plus 2AS. So V squared equals 20 times 9.81. Go on, give it to me. 14.14? For 14 meters per second. That's the V squared, is it? So that's the V.
Keep it V squared, we use V squared.
I know. So, no, leave it, it's fine. So then what's the formula for kinetic energy?
Half of V squared.
A half V squared, which will be 98.1 joules.
Half of V.
Yeah,
Right.
I just did.
There is no point now.
Close enough. Yep. Okay. So if you want, you can write this one down, and we'll have a look at another example now. You don't need to write down that bit I did at the end. I only did that for Faisal because he wanted to see it. Right? Yeah. So it's just this part that you really need. You have a question. I can sense it.
No.
Are you sure?
Yeah.
Okay. It's okay? Go on, get off the phone or I'll take it.
How?
How? Well, I'll come over and I'll take it.
No.
Then put it away.
No.
Okay, you got that now?
So basically,
I knew it! I knew before you knew you had a question.
let's try to put it in words.
Yes.
The ball, its potential energy is basically the ability for it to fall.
Yes. Yeah, pretty
That's
much.
the potential energy.
Yeah, because it has an ability to accelerate. It's going to fall and hit the ground. So its potential energy is like this ability. Yeah. Now the reason it has this ability is because the Earth is pulling it down. If this was in outer space, then it loses this potential energy because it won't suddenly fall. It'll be floating. Yeah.
So does that, but potential energy is cancelled in outer space, or is it negative potential energy as in trapped?
Good, very good. It depends on your point of view. So if you're just looking at something floating around in the International Space Station, you would say it has no potential energy because it's not going to suddenly fall to the ground in the space station. However, if you zoom out and look at the total system, then you are right to say it's negative because the ball is trapped in the space station, which is trapped in an orbit. You know, so for these things, it's sometimes a matter of perspective. Yeah, how much you zoom in. Yes. Moving on.
Isn't it kinetic energy if something was moving in space?
It'll have kinetic energy. Yeah.
So isn't the potential energy changed from the kinetic energy?
Not always.
It can be divided into both.
But it might have kinetic energy if somebody just pushed it, you know. So it got the energy from the astronaut's hand.
Yeah.
Yeah.
So So the Earth has kinetic energy
The Earth has kinetic energy, yes, because it's moving. Yeah.
and potential.
And it has potential because it's trapped
Negative.
around the sun. Yeah, yeah. Okay, here, this is a good example of how you can use this to make a difficult problem simpler. So I'd like you to write this one down. It's an important example.
This looks beautiful. Yeah, I'm taking my notes of that. But I know this one's nice.
Yes. Got it? Oh, sorry. A 200-gram bullet is fired horizontally from a height of 10 meters at 100 meters per second. How fast is it going when it hits the ground? Yes? Can I do this one now?
Yeah.
Now, previously in physics, you remember we did the question starring Thelma and Louise, where they drive their car off the cliff at the end of the movie. Do you remember this question?
Yeah.
So, the car moves horizontally and then it hits the water. And we want to know how fast is it going when it hits the water. So there was quite a lot of steps there. First you have to get the time, then you have to get the Vx, then you have to get the Vy, and then you use Pythagoras to get the V. Do you remember this? But now we have another way of doing it. So, here's the bullet. It's 0.1 kg, 0.2, and its speed is 100 meters per second. And then it will hit the ground here. We can use energy to solve this. Oh, and what was the height? 10 meters?
Yes.
What energy does it have here? Firstly, does it have kinetic energy?
Yeah.
Yes, it has kinetic. Does it have potential?
At the top, yes.
Yes. Does it have kinetic here?
Yeah.
Does it have potential? No. KE1 plus PE1 should equal KE2 plus 0. What's the formula for kinetic? A half mv squared. Potential GH, yeah. Equals a half m, and we don't know the v at the end here. That's what we want. That's much easier to do. What's in common? What can we cancel? What can we cancel? No? 0.2. And also, I'll multiply everything by 2. 2, 2, 2. What happens here? Cancel, yeah, and here? Cancel. So we end up with v squared equals 100 squared plus 98.1 times 2, which is 196.2. Right. So then, finally, v is the square root of 10196.2. I've reached my limit here. What's that?
100.
It's 100.97. So it's going slightly faster when it hits the ground. much easier to do these ones this way.
So, will there be a question that would ask us to do it in the other way?
No. Usually in the physics exam, they do not specify a method for any of the questions. This is good. It means you have total freedom on what method you would like to use. Absolutely. Oh, read the question? Yeah, go ahead. Oh yeah, go back to the question. Yeah. So, does everyone have the answer? Not yet. Oh yeah. Can I go back to the question now? How many more physics hours do we have this week? 3, is it? Because we've only had 3 so far, isn't it? Yeah. Okay. You can write this down now. Right. You can start the questions now for a few minutes. Okay. No. Nader just wants to write this down. You got it? Okay. Right, I'll close this now. So if you can try these for a few minutes.